Alright guys, this is the sound wave notes video, and so you need to find the area of your notes that are sound wave notes. Also, you may want to pause the video and get you a piece of paper to write down this review we're fixing to do, and this is reviewing our last video. Basically, it just tells us and shows us everything in a big picture. Sometimes it's hard to see this in our actual notes. So let's talk about the two main types of waves. I remember from yesterday, or maybe not yesterday, but our last video, we have mechanical waves and we have non-mechanical waves. Mechanical waves require a medium. They require a medium. Non-mechanical does not. They are electromagnetic waves, so they can actually travel through a vacuum. Now, mechanical, to review them, we had two types. We had transverse and we had longitudinal. Now, transverse, examples of transverse would be surface waves. Surface waves are the ocean waves, water waves. Okay, that's just what they're called in science. And seismic waves. Remember the earthquake? So seismic waves are transverse. Longitudinal is what we're going to talk about today, because sound waves are longitudinal. Non-mechanical waves, which are electromagnetic, will come on our next video. So today we're going to talk about sound waves, so I wanted to make sure that we looked at this all again so that you're kind of seeing the big picture of exactly where everything belongs. So let's go ahead and dive into our notes. I'm going to tell you something really quick before we start. The very top of your sound wave notes are standing waves. Now, standing waves aren't just sound, so I want to be clear about that. It's actually finishing up our regular wave notes, but it just went and fit perfectly on the notes this way. So we're going to talk about standing waves, then we're going to get into more detail about sound waves themselves. All right, standing waves are formed when two waves equal in wavelength and frequency traveling in opposite directions interfere with one another. So just think about it this way. You have a transverse wave coming from the left of your screen, a transverse wave coming from the right of your screen. They have the same wavelength, same frequency, but when they hit one another, they make a standing wave. And we're going to look at one of these in just a second. These standing waves create nodes and antinodes. The nodes are the parts of the standing wave that have no vibration, and they are the points of complete destructive interference. Now, complete destructive interference, what that means, the way I remember that is, if I destroy something, there's nothing else there. Like if we have a wrecking ball that destroys a house, there's nothing else there. And so the node where is complete destructive interference, that means that there's nothing there. It's actually, there's no vibration. Antinodes are the part of the standing wave that is at the maximum vibration, and they are points of complete constructive interference. And this is where the two waves come together and actually make their amplitudes even larger because they both come together. So the way I remember complete constructive interference is if I'm constructing something, I'm making something larger. If we're constructing a building, it started as nothing, then we make it a large building. And that is an antinode. Let's go ahead and look at one of these. Okay, so for instance, the blue line up here is one of our waves. The green is the other wave. When they come in contact, they make this red wave here at the bottom. And if you'll notice, their amplitudes at the top, the blue, let's pause these so that we can look at them. If you'll notice, look, the amplitude of the blue is, well, and this may be, let's pause it a little bit better. See if I can pause it a little bit better. Nope, I didn't really. Anyway, the amplitude of this wave is going to be different than the resultant wave, right? Because they've actually created larger amplitudes at times, but then they've also created nodes, which are no vibration. So let's see. Okay, let's look at this. With these two waves right here where they come together is going to be the node, complete destructive interference. Right here is where they come together and make the antinode, which is complete constructive interference. Do you see right here how the amplitude of the resultant wave, once they're all together, is it's really close to 10, whereas the amplitudes by themselves are 5. So they've actually doubled their amplitude. By coming together. So a standing wave, when the two waves come together, actually they can double their amplitudes, but then they also have these little areas right here are areas of destructive interference, and they are called nodes. So these are your examples of a standing wave. Okay? Now let's get back to our notes. Now we're going to go into sound waves, and the rest of our notes are going to be talking about sound waves, so let's go ahead and get started. Sound waves are in air, that's the medium they travel through, and they can spread in all directions. Now, how loud a sound is depends on the amplitude of the sound wave. If the amplitude is larger, it's going to be a louder sound. If it's smaller, it's going to be a smaller sound. Or I'm sorry, not a smaller sound, but a softer sound, or it's going to be harder for you to hear. Now, the speed of sound in air, if it's at room temperature, is 346 meters per second. And the speed of sound waves increases as the temperature of a gas increases. So the speed of sound is going to be faster in a warmer room than it will be a colder room. A colder room slows it down. So the way I remember that is I get slower in cold weather. It makes me, it's almost like if you're freezing something, the molecules, remember, start to slow down, so it's harder for things to move in there. As you increase the temperature, like increasing the temperature of the gas, the molecules can move faster, so the speed of sound can move faster. Now, the speed of sound is faster in liquids and solids than it is in gases, and we've already talked about that the speed of any wave can actually be faster in gases than it will be, faster in solids than it is in gases. Now, let's talk about the Doppler effect. This has to do with sound waves, and the pitch of sound waves, whether it's a high pitch or a low pitch, is determined by the frequency at which the sound waves strike your eardrum in your ear, okay? And frequency is how fast a wave goes in a period of time. If you'll remember, we talked about that. Now, when an object is moving, the frequency in front of the object is higher because the sound wave's being compressed, and the frequency behind the moving object is lower because the sound waves are spread out. So let's look at a picture of that. Now, I know my drawing is pretty terrible, but this will help hopefully give you a visual. If this is an ambulance with a siren and it's driving down the road, the red lines are my sound waves from the siren. So the siren is sounding, and as the ambulance moves down or drives down the road, it pushes those sound waves together, giving it a higher frequency. That means more waves are happening in a period of time, and so there's a higher pitch. So when an ambulance is traveling towards you, you hear a really high pitch. Once an ambulance passes by you, the pitch lowers because behind the ambulance, these sound waves have spread back out. So they have a lower frequency, which means they have a lower pitch. Now, when an object is moving, the wavelengths in front of the object are pushed together. That gives it the high pitch, and the wavelengths behind the moving object are more spread out, which gives it a low pitch. Now, let's talk about pitch. We've actually already talked about pitch a little bit, and pitch is how high or how low a note sounds. Pitch is related to the vibration and the frequency of sound waves, which we've already discussed. If you have a high pitch, that means something is vibrating very fast, and it's a high frequency, which would be something, an example would be a violin. If you have a low pitch, things are vibrating very slow. You have a lower frequency. An example of that would be like a cello. Now, humans hear at a frequency anywhere between 20 and 20,000 hertz. That's the hearing range for humans. And so if you're below 20 hertz, something that's below 20 hertz would actually be able to hear infrasound, because we can't hear it, but some animals can hear it. And if you're above 20,000 hertz, then that's called ultrasound, and we can't hear it, but again, some animals can hear it. Elephants, I believe, are the ones that can hear infrasound below 20 hertz, and then dogs, you know, those real high-pitched dog whistles that we can't really hear with our ears, are ultrasound, and dogs can hear the ultrasound. Now, let's discuss resonance. Resonance is the ability of two objects to vibrate by absorbing energy at their natural frequency. So whatever their natural frequency is, if they're able to vibrate by absorbing energy, that's called resonance. Complex objects have many natural frequencies, so they resonate very well, and they can have all different types of pitches. An example of that would be an acoustic guitar. Now, some objects do not resonate well, and they actually have to be amplified electronically because they do not have all of those natural frequencies. An example of that would be an electric guitar. Now, let's talk about sound reflection. And reflection is actually an interference with waves or of waves. And we're going to talk about this in more detail in another video, but we are going to talk about sound reflecting for a moment. If you shout over the edge of a rock canyon, the sound may be reflected by the rock walls. And what do we call that? We call that an echo, right? So what happens is your sound waves from your mouth as you yell goes and hits the wall, and the sound waves bounce back. That's them reflecting, okay? And then we call it that we've heard an echo. So reflected sound waves are used to determine distances and to create images. This is actually how we use sound in different areas of our life, and let's talk about that. The ways we can do that are with sonograms. Sonograms are those that you can use to locate objects by sending out sounds and interpreting the waves that are reflected back. Women get sonograms when they're having a baby, and they are able to see the picture of their baby. And the way that happens is the sonogram sends sound waves in to the stomach of the woman, and then they bounce back at different times. When the sound wave has hit the baby and comes back, it kind of like places a dot as the picture. And all those collective dots then create the picture that the woman can see of her baby. Sonar is another way we use sound. And sonar is a system that uses reflected sound to measure distances. Sonar is what submarines have, because submarines want to know how far away a boat is or another submarine is so that they don't run into each other. And how a sonar works is they send out sound waves, and when those sound waves, depending on when they are reflected back, it tells them, because the sound wave is sent from the submarine, it hits maybe the boat that they're trying to figure out how far that boat is, hits the boat, comes back, and they're able to determine by the sonar how far that boat is. So waves that produce pictures of internal structures can also be used to treat certain medical problems. So sonograms can also be used to find medical problems that you might have, like a tumor or something like that. Kidney stones are also, they're treated with this. You can find where your kidney stones are. They can draw a picture of how large the kidney stones are so that they know what type of medical procedure to do for those kidney stones. And I believe this ends our video for sound waves. So this is what I'd like you to do. I'd like you to write down sound and do an acronym with sound, telling me the 1, 2, 3, 4, there's 5 letters in sound, so telling me the most important 5 things that we learned about sound in this video. Have a great evening, and I'll see you in class.